This is just stating the sampling theorem using our frequency analysis of this most basic system. And so I have to sample at a rate greater than twice the highest frequency of the original signal. And the key thing is I recover all the points in between exactly. The big if, don't forget, is the signal must be strictly band limited. It can have no frequency content higher than B hertz. So the final detail where this differs a bit from the original consideration of sampling that when we talked about sampling analog signals is that the star transform is restricted to causal signals, x of t. And so all the things that we talked about when we originally considered a sampled signal xs of t, we really didn't restrict that to causal signals. And so here we've taken the same figures, but we've indicated with the x outs that we are no longer, when we talk about a starred transform, we no longer are considering a signal that is non-causal. And so this is the extra restriction of the starred transform. It's restricted to causal signals x of t. And so the Laplace transform of that sampled signal, which is x star of t, is now the starred transform x star of s. And so we can consider this the starred transform or sampled signal in time, and taking the Laplace transform of the signal, which is just the continuous signal times the impulse train, again with the restriction that this is causal. So it only exists for t greater than or equal to 0, which now is just the sum of that signal times the impulse train. The Laplace transform of this is x star of s, which is our starred transform, which is the sum from minus infinity to infinity of x of nt0 e to the minus nst0. By the way, if since x of nt0 is 0, we can just take this sum from 0 to infinity also. But to be consistent, we'll just keep that in mind that this only applies to causal signals. And so so the Laplace transform of the zero order halted signal, so output x 0 of t, so we'll call that the output of a zero order hold. Recall that in the system diagram, so this output x0 of t has gone through the zero order hold, so it's x star of t convolution with the zero order hold transfer function. And we saw earlier that's a rectangular function delayed by half the pulse width and with a width t0. And so again, that's the output is now the convolution. And so we just denote that as x0 of t, the output of the zero order hold here at the output. So now we can take the Laplace transform. So the x0 of s is our output spectrum out of the zero order hold. So it's the starred transform of the signal x of t. So that's just the Laplace transform x star. And then since it's a convolution in time, I multiply it by the Laplace transform of a zero order hold, which is 1 minus e to the st0 over s. So this is just the Laplace transform for the zero order hold, or the rectangular pulse that we have shown below. And so it's straightforward to take find the starred transform of the sampled signal, which we denoted as x star of t. And finally, the output of the zero order hold just follows from the normal properties of Laplace transform. One last thing, do not confuse this star as a conjugate. This is not a complex conjugate. This is a star transform notation. So x star of s, x star of t. Both of those indicate star transform. Uh, so somehow in working with the star transform, the context of the discussion or the context of the derivation, it should be clear when you're using star transform as opposed to when you're doing a complex conjugate. And so that can be a little confusing at first, but as you work with this more, you'll know when a star transform is meant versus a complex conjugate. So again, same pictures as we saw with sampling a general signal, but now these are restricted to causal signals for the star transform. So when we use the star transform, from here on, we're going to restrict it to a causal signal x of t. And so it's 0 for any time less than 0. Whenever we say a star transform, we're already going to imply that the function is causal and may arbitrarily be multiplied by the unit step then. So later on, we're going to use the two-sided Z transform to obtain a star transform. Whenever we do that, since the time domain transform is causal, the course, because of the star transform, then of course the two-sided Z transform must also describe a causal function. And so we can multiply that function also by U of n. So with these interpretations of star transform that it's always dealing with a causal function, the derived results are going to be the same whether or not I use a one-sided or two-sided Z transform or Laplace transform. Because the difference between one-sided and two-sided transforms is one starts at 0 and the other goes from minus infinity to infinity. Well, if everything is 0 for t or n less than 0, then the transforms are the same. So this makes the use of the two-sided Z transform a little more straightforward. Just perhaps to be cautious, maybe just multiply by U of n or U of t to make sure you retain causality. So the star transform, which is again the function times the impulse train. Again, x of t must be causal, so I can arbitrarily multiply by U of t. Nothing should change. And then I can just expand the impulse train minus infinity to infinity. Often we retain the minus infinity to infinity because the Fourier transform of that infinite impulse train from minus infinity to infinity gives that that function that is an impulse train in frequency that is often just useful to use. I could restrict this to 0 to infinity, but I would lose perhaps the advantage of taking the Fourier transform of the minus infinity to infinity form. And so this can also, again, be written as x of t, just the sum from 0 to infinity. Again, with perhaps losing, or perhaps the weakness of not being able to use a Fourier transform pair as straightforwardly. And so we can rewrite this and incorporate the U of n's too. So again, the star transform, x star of t, the sampled signal in time, restricted to causal, of course, when I use star transform notation, gives a Laplace transform, x star of s, which is 0 to infinity, the times the samples, e to the minus nst0, just a Laplace transform of the sampled signal. And again, I could use minus infinity to infinity with the unit step. This is the Z transform of x of n u of n, x of n being the samples, which equals x of n t. times the unit step to short causality, because now we're using a two-sided zero transform in general. So it's always good to multiply by u of n. And again, now we would replace z equals e to the st0, again using our relationship between z transform and Laplace transform to obtain the Laplace transform from z transform. So again, don't forget, star transform is restricted to causal. Safe thing to do is multiply through by u of n's to kind of remind yourself when you're first using this. And in control systems, often the z transforms they use are unilateral z transform. However, we're going to be using the bilateral z transforms. And so when we use the z transform, we should multiply by u of n. Very few authors use a bilateral star transform and typically restrict signals to causal signals, as we've shown above. So each of these signals, again, we could take the appropriate Fourier transforms to find x of omega. Again, we're showing the two-sided function, but we're going to use x-outs to indicate, of course, that the net star transform function x star of t is now causal. And so a good way to do this is restrict x of t to be causal, so that when this multiplies the infinitely long impulse train, everything becomes zero to the left side of zero. And so again, we kind of mentioned if we use the two-sided infinite impulse train, then when we multiply these two together, we get convolution in the frequency domain. And of course, the Fourier transform of the two-sided impulse train is this nice and convenient two-sided impulse train in frequency. But now, again, we get duplicates of the spectrum at each of the impulses. And so we can see that our star transform output has the same form as what we considered with the two-sided inputs, but now we've just restricted x of t to be causal, and so we lose the left side of the picture. And so everything starts at zero, and everything looks much the same in terms of the Fourier transforms. Again, do not confuse the star transform with a complex conjugate. This is the star transform that we're denoting here in both locations. So we can go through the whole sampling diagram with our notation indicating that the output of the sample signal is now x star of t in time or x star of omega in frequency domain. And so again, go through all the steps, finding the Fourier transform at each step. Again, we use the x-outs to indicate that these are causal now, just by setting x of t to be 0 for t less than 0. Nevertheless, we take a Fourier transform. It's just easy to draw a spectrum. Again, Fourier transform, we leave this two-sided. It doesn't affect things because when I multiply it by x of t, I still, since x of t is 0 on the left, the net result is 0 on the left. So the Fourier transform, the impulse trains, again, impulse train and frequency, where omega 0 is 2 pi over t0, the sample frequency, sample period. And again, the weight of those impulses is 2 pi over t0. When I do multiplying in time to get the output x star of t, its Fourier transform is the convolution of the two above. So I get a duplicate of the spectrum again, a over t0. I have a 1 over 2 pi in that convolution, so that's where the 2 pi disappeared from this 2 pi over t0 weight. Finally, right at the last step, I pass the signal through the filter with impulse response that's a rectangular pulse, h of t, of height 1 and width t0. And the Fourier transform of a rectangular pulse is a sinc function with a magnitude t0. There is a time delay and a phase term here, so I'm just plotting the magnitude here. Finally, these two signals are convolved to produce the final digital stepwise output. First thing to notice is that everything is 0 on the left, so everything's now causal because of the original multiplication with x of t being 0 on the left. In addition, I can take the Fourier transform of this stepwise signal is the product, since it's a convolution in time, it's the product of these two spectra above. Since the function again is flat near 0, I get the original spectrum, almost a perfect replica down near 0. The t0 cancels the 1 over t0. The t0 from the sink cancels the 1 over t0. And in addition, notice that the other periodic replicas are in regions, multiples of omega 0, where the sink functions passing through 0 are very small. And so I get just some small remnants of spectra out here, which can be thought of as the components of the frequency spectrum that make up the difference between the original smooth signal and its piecewise or stepwise version. So we can also consider starred transform. Instead of a zero order hold, we could consider perfect reconstruction filter. Again, that's ideal low pass with cutoff frequency half the sample rate. And the starred transform, going through that, of course, produce exactly the original output signal y of t would equal to x of t. Again, with starred transform, don't forget, so we've indicated here, starred transform is restricted to causal signals, and so we just kind of put an X out as kind of a reminder that when we consider the starred transform, we have causal signals at all the points here. The only exception is for convenience, we use the infinite impulse train, but of course when we multiply it by 0 due to x of t here on the left, produces the same output as a one-sided impulse train would. So the starred transform again generally deals with a causal signal, and so just to kind of keep the link back to the original analyses, we kind of show the X out, deleting the non-causal portions. And so in the time domain, again, the ideal low pass corresponds to a sink type impulse response. And so when we have our causal signal at the input multiplying the impulse train, the impulses to the left of 0 disappear since they're multiplied by 0 above. And then similarly here at the output. However, the same interpolation notion view can be used, and that at each impulse in the sampled signal, it's interpolated by the sink pulses, the impulse response of the filter. And so that fills in and computes the, produces the original value of the signal x of t. So the final output, of course, will be the reconstructed version y of t equal to x of t. And again, because the signal is 0 to the left, we would see a causal response at the output of the system. So the Laplace transform, the zero order hold, we've already used it. Just quickly show where that came from. The easiest way to do this is to consider, again, the zero order hold is this pulse that starts at 0 and ends at t0. We could use the pulse or capital pi or gate function as our defined pulse to define it, but we could also define it in terms of unit steps. And so that's probably the easiest way to derive the Laplace transform. So we have the Laplace transform of a unit step and a unit step delayed by t0. Well, the Laplace transform of a unit step is 1 over s. And so I would get